Very good. All right. So the topic that was in your schedule was called Project X-Ray and FASM. And as I said, these are examples of free open source software for FPGA design. I'm going to give sort of some background on open source. We'll get to the Project X-Ray FASM here in about 7 or 8 minutes. Okay, so there we go. All right, you know, there's a lot of open source software out there, and some of it is very high quality. What's the most well-known piece of open source software that you all have used many, many, many times? Linux. How about Linux? Okay, when I was a student, Unix had been invented at Bell Labs. It was owned by Bell Labs and was subsequently sold to another company. It eventually was owned by a company here in Utah. It was a commercial product. You could not run Unix without licensing it, and it was the subject of lots of lawsuits. And somebody came along and said, this is really valuable stuff. Why don't we just create something that looks just like it? We won't look at the source code, et cetera, et cetera. Okay? Well, there were lawsuits about whether they did, but the bottom line is we now have Linux and it is open source. And does anybody worry that it's a bunch of amateurs and is low quality and is filled with bugs and security holes? No, we actually think it has fewer bugs and has fewer security vulnerabilities. Why? What would be the obvious reason?
A lot more people looking at it.
When you've got billions of eyes looking at it, using it, and examining the source code, it's pretty hard to have bugs and or security vulnerabilities go through. Now, it still happens all the time. But compare that to a team at a company with maybe a dozen people working on a project, right? Plus notions of bug fixes and updates and, you know, add-on features. So open source software has proven itself. What are some other good examples of open source software that you've probably used?
Firefox. Mozilla Firefox.
Firefox, yeah, Firefox, open source. Okay, anything else? What do you compile with? GCC, right? LLVM, these are compilers that are open source, okay? How about graphics packages? You ever heard of OpenCV? That's a graphics package, computer vision package. Okay.
OpenGL.
OpenGL, right, for graphics programming. So yeah, there's a lot of good, high quality open source software out there. Okay. Now, we've never had really open source software for FPGAs, and some people over the years have questioned, well, why should it be different for FPGAs than for CPUs? What are the issues? I will seed the discussion with the following comment. If I want to write a compiler for an Intel processor, what do I need to know?
The ISA.
I need to know the ISA. I need to know what is the instruction set and precisely what does each instruction do to the state of the machine. Do I have to know at the transistor level how all of that gets implemented in the microarchitecture? No, I don't. And the ISA is published, and therefore it was relatively straightforward to do that. With an FPGA, many people believe it's different, that to understand exactly what is down there in the lower levels, you have to know a lot more about the hardware, transistor level design, to really understand it. And so you could argue that that's one of the reasons it's taken longer. It's also a very difficult task, okay? Because you don't have this nice published high-level ISA. All right. Well, let's just talk about open source FPGA tools in general, because I've been at BYU doing this for the last 25 years. This little history is totally biased towards what we've done here, projects I've been involved in. And if people from the outside watch this, they'll go, oh, he's missed 90% of what's happened. It's true. I'm focusing on what we've done here. But the bottom line is way back in 1995, there was a machine called Splash 2. We got a copy of that machine. It was an early configurable supercomputing machine. And they had used something called readback to pull the state. Well, no, readback has always existed for Xilinx FPGAs. It allowed you to read the bit stream out of the part. But if you set the options correctly, you got the state of all the memories and flip-flops in the part as of the time you did the readback, along with the bit stream. What does that allow you to do? Extract the running state of the design, right? Okay. And we said, ooh, that's cool. And so I had some students, we wrote some software, and we started doing things with that. Dr. Hutchings led an effort called JHDL. It was a Java embedded HDL for FPGA design. And then, my students jumped on the bandwagon and said, hey, if we have readback, we already had a simulator for JHDL. We said, could we pull the state out of the circuit, shove those values into the waveform viewer, and now, whether you're watching simulation of your design or the actual execution of your design in hardware, it's the same interface, you just flip a switch. And so to do that, we had to start learning about exactly how the Verilog VHDL was mapped to the hardware. We had to learn exactly about where everything was placed, and we had to look for things that the tools left behind that would tell us how we could pull these values out of the bit stream. So we were doing this a long time ago. Okay. Then come along, and then other students followed. We had a student who said, well, if I can pull the state out of a running FPGA, I can context switch calculations on a physical FPGA. And he demonstrated doing that clear back in about 2000. Okay, then along came Chris Lavin in 2010. He created something called RapidSmith. And it was a way to export designs in and out of the Xilinx flow. And it relied on something called XDL and XDLRC, and it gave us tremendous capabilities to analyze, create, modify, or rapidly prototype up new designs without going through the standard synthesis, place and route process. But it relied on these two things from Xilinx, okay? So here's a picture. Basically, and we're going to refer to this, so we're going to go through it quickly. When you do a design and you map it, from using Vivado, you start with synthesis. Then you click a button called implement. And implement actually, depending on how far back you go in the tools, what gets done in each box has moved around. But in general, implement takes care of what we call packing, placement, and routing. And when you're all done with that, you have the completely implemented the design, and then you've seen the BitGen button. And what XDL allowed you to do was pull the design out of the Xilinx flow at any of these points, put it into your own CAD tools to do anything you wanted with it. And if you could convert it back to legal XDL, you could re-import it back into the flow. I'll give you two examples where this was helpful. Chris, who did this work, what he was really interested in was answering the question, how rapid prototyping flow could you create? How quickly could you go from a design specification to a placed and routed design? Can you do it in 5 seconds? Can you do it in 5 minutes? Or does it have to take, much, much longer? And so he created this tool to help him with that piece of work, okay? Because what he did is he had little pre-placed and routed modules that he literally tiled out across the FPGA, and then he just had to run the wires that interconnected those blocks. So he was routing a few thousand wires and could create this very large design very, very quickly. And then he would use XDL and shove it back in and have Xilinx generate the bit stream. And he demonstrated, 75x speedups over the equivalent compilation flow with Xilinx tools. But of course, he paid a performance price, blah, blah, blah. Standard, kind of thing. Okay. Second analysis that you might want to do. Dr. Wirthlin does reliability. So Dr. Wirthlin, some years ago, said, we're finding in our beam test that certain things turn into reliability failure points. Well, we built custom CAD tools that could remove those failure points from the design. Oh, they're doing their VCC or grounds using this funny thing called a weak keeper. We'll go find them all and remove them. We will modify the design. So he would pull them out, usually probably after placement and routing, do some changes, shove it back in. So those are the kinds of things that people would have wanted to do over the years with custom CAD tool flows. To do things that a standard synthesis place route bitgen doesn't support, okay? All right, then, things came along. Vivado appeared. We did additional work. I had students who did something called RapidSmith 2, kind of trying to do the same thing, but without XDL, okay? In 2015, then, along came something that we're going to talk about in a minute, so I put it on my timeline, even though there are lots of other things going on at the time. Something called Project IceStorm, where they documented the entire bit stream for a company named Lattice's FPGA parts, and they created some software to allow you to read and write bit streams, convert netlists into bit streams, etc. And so they actually demonstrated going from, that was not Vivado to bitstream, that was Verilog to bitstream. That's a typo right there on the slide, sorry. And then in 2018, I had a student, Dallin, who went from Verilog to a bitstream. The way he got there is that by then we had learned about something called Project X-Ray. And we said, well, there's open source synthesis tools. We now know about the bitstream, and we already had RapidSmith 2 with packers, placement, and routing tools. And so he demonstrated a full Verilog to bitstream flow. Okay. The point of all this is to show that people have been doing things like this for years, but we were always sort of using whatever we could get out of the commercial tools to help us understand how things have been mapped. Okay. In parallel with this for many years has been a project called VTR. Although in the olden days it was called VPR, and then when they wrapped VPR with other tools, they called it VTR, and it's a total source of confusion. People use the terms interchangeably. If you go to the VTR homepage, though, under the list of major contributors, the name Jeff Goders appears because he did this in his master's thesis up at, that was at Toronto.
Yeah, UBC.
UBC, okay.
Only a little piece.
Okay. Oh, he did some good work. So VTR was a CAD tool flow, had been invented so that people could experiment with CAD tool flows as well as experiment with synthetic architectures, not commercial architectures, but architectures that you could describe with some XML file. I got a grid of this, and here's what all the building blocks look like, and here's what all the wiring channels look like. And so over the years, people published thousands of papers using this VTR flow. But in general, VTR was never targeted at generating designs for commercial FPGAs. Okay, and if I'm not mistaken, it never had bitstream generation. Yeah, so you would take your designs, you'd run all these designs through, and you measure how big and how fast they would run and how long the CAD tools took, and that would be the product of that. So that has been going on for years, and it was it intersected with those of us attempting to target commercial devices, some, but not a heck of a lot. Okay. So here's a picture of the VTR VPR flow, and all I want to point out is traditionally they've started with HDL and gone down this path through the green and the brown to give you all this, all these metrics and measurements of your final design. And they would take in an FPGA architecture description to do it. But in recent years, they have added other paths so you can take other kinds of tools for parts of the flow, and you could go back and forth between other tools. So now it's being opened up and other people could start to plug things in. That will come back in later before we're done. Okay. Here's the Project IceStorm. I just thought I'd put a slide up. They were kind of the first to completely document a bitstream format for a part, make it publicly available, and then write tools. And so they have a full flow, synthesis, place and route, and then bitstream generation. So they can go from Verilog to bitstreams for these lattice parts. Okay. So we learned about the SymbiFlow project, Mike, how many years ago? It's got to be 3.5 years ago, 4 years ago. I'm still unclear when it officially started, but this is from their GitHub page, an open source flow for generating bit streams from Verilog. And their target is to be able to support lots of FPGA families and to be able to support all the features of FPGAs. SymbiFlow is the organization. Project X-Ray, which we're going to spend the next half hour talking about, is one of the sub-projects inside SymbiFlow. But you can see they have 73 repositories, so it's a big project.
Did IceStorm get put in under SymbiFlow as well? Like,
No, IceStorm is kind of on its own still. Yeah, if you do a search, you'll find it at different locations, okay? But there has been cross-pollination between the groups.
Doesn't SymbiFlow also support Lattice?
Nope, SymbiFlow is really focusing, from what I can tell, mostly on Xilinx parts right now. But I could be wrong about that. But the corner of SymbiFlow that we've had our interactions with have been focused on Xilinx parts. But notice, 73 repositories. There's a lot going on here. Okay? All right.
There may be some Lattice with Project Trellis. Is that what it's called?
Yeah.
Is Trellis in SymbiFlow? I think it
I
might be.
think it is. Yeah. And so then the question is,
Not the ICE parts, but the DCP or
the
something.
DCP5s or something?
Yeah, something like that.
See, like I say, I know there's been some overlap, and I'm not terribly up to speed on that. Yeah.
It doesn't support like the ICE40 FPGA?
No, that's IceStorm.
IceStorm is the
It
ice.
doesn't live here.
Okay.
Yeah.
But they do contribute to it.
Yeah,
It's-
yeah.
it's there.
There's
Common people.
a lot of common people in
I'm
overlap.
sure.
Okay. So we're going to talk about X-ray for the next 20 to 30 minutes. Okay. So they have a GitHub repo. It's called SymbiFlow/Project X-Ray, and this is their page, documenting the Xilinx 7 series bitstream format. Okay. So, and in the repo, you'll find tools and scripts that allow you, if you wanted to, if you ran all their scripts, when you were done, you would have a database that would tell you what all the bits in Xilinx 7 series bitstream do. And you'd be able to say, well, there's the bit that programs that mux, and there's the bit that's part of the ALUT lookup table contents that we talked about last week as we were talking about the different configuration bits. Okay. They have documentation. You remember we learned about Sphinx from Dr. Worthland? Yeah, if you click on this docs button right here, it will take you to a bunch of Sphinx generated documentation. Okay. They have pre-built databases of bit streams for some parts, or you could generate your own. Okay. So let's talk about this. So, well, hang on. Before we get there, I'm going to talk about a few other things. So Project X-Ray is documenting the bit stream. But if we go way back to my picture from the RapidSmith slide, is bitstream generation an entire CAD flow? No, it is only the final step. But it's the step that was the longest in having an open source solution. People have been writing placers and routers and synthesis tools for a long time. But this is just the bitstream part. So if you want to have a total flow, which is what the goal of SymbiFlow is, you're going to have synthesis tools and place and route tools as well. So one of those is called Nextpnr. It's a group who is working on, now you notice they're working on Lattice parts, but here at the bottom it says they're working towards support for Xilinx. So they have their approach to doing placement and routing for parts. And so there is a group who's working on taking a synthesis tool and Nextpnr and Project X-Ray and eventually having an end-to-end flow. There are other people who are pushing on a synthesis tool plus VPR for the placement and routing and Project X-Ray for the bitstream generation. So you can mix and match tools and come up with lots of flows, okay? But the two that I'm most familiar with are the VPR plus SymbiFlow to create an end-to-end flow, or the Nextpnr plus SymbiFlow to create an end-to-end, okay? So let's look inside Project X-Ray. Okay, let's see, what do we got? Okay, so now I don't have much in the way of slides. Let's talk for a minute about how would you go about documenting what the bits in a bit stream do? This is, I believe you would call this black box testing, right? You put stuff in and you look at what comes out. And if you're smart about it and you do it enough, you should be able to come up with a reasonable model of the mapping from inputs to outputs. So here's an example. Take one of your designs from 220, okay? Doesn't matter what the design is, okay? And now this is very simplified, but to give you the idea. And there's a particular 6-input LUT in there, which has been, which has been programmed to be some logic function. Okay, go into the tools and change one of the configuration bits in that LUT from a 0 to a 1 or from a 1 to a 0. Take the bit stream of the before and after and compare them. And if you know how to filter out all the other stuff that's in the bit stream, which isn't the actual configuration bits, there's addresses of parts of the chip as it sets the address of where it can go configure. And there are checksums, et cetera, but if you can isolate and get down into the actual configuration bits, if the only thing you did is change a LUT programming bit from a 0 to a 1 or a 1 to a 0, then the difference should be the thing that controls that particular configuration feature. Would you agree? Okay. Another thing, you take a design and you take a wire and it's going from point A to point B and it goes through this LUT. Okay, I'm sorry, it goes through a particular pip. Same thing, you could change the route to go through a different pip. Okay, and now you would see some bits change, and the question is could you tell which one's turned off that pip and which one's turned on the new one? But conceptually, are you getting the idea? You make changes to the input, you look at the output, and you can start to create a mapping. And so the way a tool like this, it uses something called fuzzing, which is you take something and you make lots and lots of small changes to it. You record what went in, you record what went out, and then you start doing a differential analysis. And you can, in general, come up with the mapping, okay? So what's the net result of this? It's a bunches of files that basically say that LUT programming bit is in this location of the bit stream, and that bit is here, and it's just a bunches of files which are a table, okay? And that's what we get with Project X-Ray. So I thought what I would do is I just walk in and we'll look through the database for a few minutes to give you a feel of how it works, okay? So let's go here, and let's go, okay, so the first thing you need to do is for a given part, you kind of need to figure out how the part's organized. FPGAs have rows and columns. They have clock regions, and all of those contribute to how the bit stream is structured. And so in the database, I will make this bigger because I'm assuming the people in the back really can't see it. Okay, here, we don't even need that. Okay, so this is called part.json, and it's a part of the database, and it tells you what's inside, so the global clock regions, there's a bottom region, there's a top region. Within the bottom region, there are some rows. They're numbered. There are different configuration buses. How many frames are in each column? It's sort of giving you the overall high-level structure of a bit stream, okay? All right. I don't know if you know much about I/O banks, but there are I/O banks in these parts, and I/O banks have certain restrictions, and so they've also gone through and figured out something about the I/O banks, okay? The next thing you do is you have to figure out which tiles are at which location in the FPGA. In other words, we're going to create a map that says there's a CLB tile here, and next to it is an interconnect tile, and next to that is a BRAM. And so you build something called tilegrid.json, which for every tile says, well, there's a tile called this, and you can see that his address is embedded in the name. Okay, and by the way, the configuration bits for him hang off of the CLB I/O clock bus, And oh, by the way, there's this base address. And if you know the base address and the number of frames and the offset and the number of words, then from all of that information, you can figure out which bits in the bit stream relate to this CLB. Okay? So you can see that the CLB below it has slightly different base address frames, offset, and words. But the point is, it isn't like there's a region of bits that just configure that CLB. It turns out that there are a whole boatload of frames. There's 36 frames, and how big is a frame? I forget. It's 101 32-bit words.
101 32-bit words for the 17.
101 32-bit words is a frame. This CLB gets bits to program him from 36 different frames, but he only has 64 bits per frame. So, this is helping you understand how they're all, spread out, but how you can zero in on the bits for a given tile.
So the bit stream, as you were talking about, so is it separated kind of more nicely into bytes and words? Is it not so much like squished together a bunch of bits, or is it?
Well, when you read it, yeah. So they've chosen to describe it as a bunches of frames, and within a frame are words. And then within the words, which are 32 bits each, there are specific bits.
And, we could have a whole
We could have a
tutorial just on the bit stream, like the format. I'd be happy to do that.
Yeah, that would be a good thing to do for those who were interested. But yeah,
That's documented, right?
Well, the general organization.
yeah, the organization is documented.
And all of this just comes out of Avado with Tickle if you wanted, right?
That's right.
There's no black box testing yet. This is just,
This,
No,
this
there is some black
this is
box
definitely
testing
not out of
come
Avado.
up
Oh,
with-
okay,
with
okay.
This
those-
is not out of Avado. One
I
thing,
eat
by the
my
way,
words.
the base, just to be clear, the base addresses are not sequential. One thing that's confusing, you think that the frame addresses are sequential. That's not the case. There's all this
It jumps around.
jumps around
So
for,
without a map, it's really hard to tell what's in a bit stream.
this is not something at all.
Yeah. Okay.
Could we ask you about your VS Code extension that gives the git blame message here?
I have no idea. It just happens. It just happened. I have no idea. Yeah,
Some extension you got turned on there.
I guess. I honestly don't know. Notice it tells us a clock region. It gives some grid locations, tells us a bit about pin functions, tells us what sites are inside that tile, and gives a tile type. So this is a pretty detailed map about what's in the FPGA. Now, a large chunk of this, not a large chunk, a bunch of this information, we always were able to get through XDL. XDL gave you this tile grid, and it told you the tile grid name. It told you all about it. It told you what sites were in it, what wires, yada, yada, yada. I think, the added information that you don't get from XDL is a lot of this, base address stuff, okay? So at any rate, so that's called tile grid. Then you go into something called the segbits file, because every CLB_LL tile in the part is the same. It's a cookie cutter approach to assembling the FPGA. So once the tile grid tells you where all the tiles are, then to figure out, okay, well, what are the bits for that tile? You just go to the segbits specifically for the CLB_LL tile type. And if you take the numbers it gives you and you combine it with these, you can zero in exactly where in the bit stream a given feature is documented. Okay, so here's just, I just paged down out into the middle. So what do we have? Well, here's the A LUT init bits. Remember, a 6-input LUT will have 64 configuration bits. And so we're looking at the tail end. So here's the bottom row configuration bit. Or maybe it's the top row, depends on how they ordered them. And what this says is, within a CLB_LL tile, there is a slice L, but it's the X0 slice L because there's 2 slice Ls in a CLB tile. Within him, there's an A LUT bell. The A LUT bell has an initialization string, or the initial contents, or for our purposes, the programming of the LUT. And if you want to figure out where the 64th bit is, It's bit offset 0 inside frame 34. But as I said, you have,
Word.
nope, it's a bit offset, it's a frame underscore bit offset. So what you have to do is you have to go back to the tile grid. The tile grid will help you figure out how to do the arithmetic to get to the right frame. There's only 2 words. So in this file, you should never see a bit offset greater than 63 because there's only 64 bits in a given frame for that tile. So there's some arithmetic you do, but you can, get to it. Okay, well, here's some other things. There's a thing inside the slice called the A out mux that selects between the A5Q signal, that's the output of the A5FF, or the carry output, or the XOR output. These are from the carry block out of the F7 mux, or the O5 or O6 output of the A LUT. And he's a mux that selects those. And so to select this value, this bit has to be off. Do you see the exclamation point? This bit has to be on. This bit has to be off. And that bit has to be off. So here's a case where there's not a one-to-one mapping between a configuration bit and this particular mux select. There's actually a group of bits which together have a binary encoding to select one of these inputs to be gated to the output of that little multiplexer. Okay, so that's a routing mux, and that's how he's programmed. Now, the B5 flip-flop has an initialization value, and this bit controls whether that B5 flip-flop gets initialized to a 0 or to a 1. And I don't have a clue. If you set that bit high, does it initialize to a 1 or a 0? I assume a 1 initializes it high. That would be logical, but you'd have to go read the documentation. There is a reset feature on this. Where is the reset? Does this one control reset high or low, or does it control reset is synchronous or asynchronous? I can't remember. There's 2 different bits for him. Okay, so you can kind of read what is going on just by the names of the features. But we've got all these X0 slice values, and then we've got a bunch of X1 slice values. Can you see that? Now, here's an interesting one. In a slice, all of the flip-flops are either rising edge triggered or falling edge triggered. And the way that is programmed is there's a thing called the clock inverter. And if you set this to a 1, then they're all falling edge triggered. Because all it is a 2-to-1 mux that selects between clock or clock bar. Okay? And so there's the bit that says the 4 flip-flops inside, or the 8 flip-flops inside that slice are either going to be rising or falling edge triggered. So that's the database. And so it would be a simple matter to read these files, okay, and process them and walk through a bit stream once you know the high-level organization, which we haven't really talked about. This notion of frames and checksums and blah, blah, blah. But once you figure that out, you can walk through and you can examine every one of these bits by just looking them up, and you could print a list of exactly how everything in the FPGA was configured if the database was complete. Now, at the current time, the Project X-Ray database has some holes in it. There are some tiles that have some features that haven't been documented, okay? But it's pretty darn complete. But there are, things that aren't done yet. And that's a topic of ongoing work, okay? So that's sort of what the Project X-Ray database is and what it does. So then the question comes, okay, so what do you do with it? What good is that database? What are some things you might do? Anybody?
Write software that create the bit stream.
Okay, so write software that takes a synthesized placed and route design and generates a bit stream. Good, okay? That's a good one. Anything else you can think of you might do with it? Okay, yeah, you could check a bit stream. Maybe somebody has corrupted your bit stream. Maybe they've thrown a Trojan in there.
Short circuits.
Yeah, maybe somebody's been filling your bit stream with short circuits. Okay.
You can also compare two different designs or two different bit streams.
Okay, you compare two different bit streams. Yeah. Okay.
Also, we'll do like certain optimizations on the results.
You might could do some optimizations. Yeah. Okay. How about the following? I have a design, and I know that it has an FPGA with a bit stream in it, but I purchased it, or some contractor developed it for me, and it was a long time ago. And I have no idea if the bit stream is really what I wanted. How do I know that somewhere along the design or tool chain, somebody hasn't added stuff to my bit stream I don't want? It's a security issue, right? And there are people who would like to know, has my bit stream been tampered with? Does it have circuitry that I probably don't want in it? If all you have is the bit stream, then what are you going to have to do? You're going to have to start with the bit stream and figure out how to look at all the bits that are turned on, and from that, create a schematic from the ground up. And then try to reason about that to schematic to make sure that, yeah, this is just what I wanted. You know, this is a stereo vision thingy or whatever, you know, for my helicopter. And there's no Trojans embedded in it. And that's not a hypothetical, you know, research project. We have a research project doing that right now. Okay, I have one where, yeah, the people funding us, they want to be able to analyze bit streams for cases where they no longer have the original HDL source. Or even if they have the HDL source, how do you know that bit stream matches that design? Well, Dr. Coders has had projects looking at that problem. But the point is, yeah, there's all kinds of things you might want to do if you have such a database. So that's
Add another one.
okay.
If you find that a fancy TMR design fails at the beam and you know which bits cause it to fail, and you want to figure out what actually happened to your design.
There you go. Do you guys know what he means when he says that TMR fails in the beam? So he has projects where he's building designs where he will replicate the circuit, maybe 3 times, take the output of the circuit and put it into a voter. And so to be able to say, man, every time that bit gets corrupted, my whole TMR design fails. This gives you a way to work backwards and say, oh, that's a problem. And then you would take a tool like what we showed earlier and take the design before you generate the bit stream and modify the design so that that particular vulnerability does not show up in the placed and routed design. Does that make sense? Okay. So yeah, there's a lot of uses for this, okay? All right, so the last thing we were going to talk about today is FASM. And then on Friday, we're going to talk about a number of other projects within the SymbiFlow umbrella that are related to Project X-Ray. Many of them build on it or contribute to it. But today I just wanted to talk about FASM. So FASM stands for FPGA assembly, okay? So here's a very complicated diagram. Okay, this comes off the FASM repository documentation. FASM is a SymbiFlow repository, okay? So let's just start here on the left. So I can start with Verilog, System Verilog, or VHDL. And there's lots of ways I can process it, and this doesn't even enumerate all of them. One of them is hand my Verilog to Vivado and synthesize, place, and route it, generate a bit stream, right?
It doesn't show, I don't understand the geometry there.
Yeah, so
Is that supposed to connect somehow?
well, that's the problem. It's incomplete because you can go from Verilog through Vivado directly. But what they've shown here is you've got lots of tools that can do synthesis. Okay? These are all open source. Well, most of these are open source tools. Quartus is the Intel tool. But the point is you've got synthesis and tech mapping tools that can take HDL and they can output various representations of the synthesized design, okay? Now, what is tech mapping? A synthesizer might simply convert your design into AND and OR gates combined with flip-flops. But you know that FPGAs don't have individual AND and OR gates in general. They have lookup tables, right? It's not universally true, but it's absolutely true for the parts that we deal with. And so tech mapping takes clumps of and and or gates and squishes them into lookup tables. Okay, that's called tech mapping. So when you get done with all of that, you have, representations, and you can write it in something called a glyph or an eGlyph file. That's a way of representing one of these tech map net lists. Or you could write it out as JSON. You could write it out as EDIF, and Dr. Worthland is the EDIF king here on campus. Okay. Then you want to go and implement the design using placement and routing tools. And there's lots of them. Here's VTR. Here's Nextpnr. But of course, Vivado has their way of doing all that, and ISC has their way of doing all that, and Quartus from Intel has their way of doing that. But what they're trying to show here is, if you want to use VTR and Nextpnr, their proposal is called FASM, and FASM is going to be what these tools would output so that a tool like Project X-Ray could convert that into a bit stream. Now, of course, the commercial tools, they can generate their own bit streams without any help. But if you're going to use, and so they're calling these bit stream generation programs FPGA assemblers. And so Project X-Ray would be an example of one of these. So FASM, FPGA assembly language. Yeah, it's that thing that you can use to generate the final executable.
That closed one you got your mouse on. I've never even noticed that.
This one right here?
Yeah.
Oh,
Is that BitGen?
No, but BitGen's like,
BitGen's part of Vivado. All I can figure, Jeff, is that they were trying to show that you might have open source ones and people might create closed source ones. That's my guess. I don't
anyone
know.
who knows FASM isn't going to bother making close.
No. I mean, yeah. I don't know if these exist, but
They couldn't decide between the S and the Z in FASM? Is
I
that?
don't know. I don't get that either.
They
That was
decided to have both.
But the point is, they're hoping that FASM could be an intermediate format. So if you work in this field for very long, the first thing you learn is when you start plugging tools together, you spend possibly half of your time figuring out what the intermediate file formats are going to be so that tool A's output can be consumed by tool B to continue the process. Because how you describe a tech-mapped synthesized net list is very different than how you would describe a placed and routed design. And over the years, there have been hundreds of ways of describing these various things. And so they're saying, no, FASM is going to solve the problem of that last representation before you generate a bit stream. That's their goal, I believe. So that's why they have this picture, okay? Now, one of the things I want to point out is just some other things we haven't talked about. Yosis is a open source synthesis tool, I believe created by the same person who was responsible for Project IceStorm. It's a pretty high quality synthesis tool. It also has formal verification capabilities now. And a lot of people in the open source community are latching onto it as the synthesis piece of this overall flow. When we did Maverick back in 2018, we used Yosis for our synthesis because it outputs a very nice format. Okay, but of course, Yosis doesn't do tech mapping. You have to combine it with a tool called ABC from, is it Berkeley?
Yeah. So to their credit, a lot of the heavy lifting is ABC. The code base of ABC is probably 10 times as large as Yosis, but
Okay. Yeah. But you need them both. You need them both to get a tech map.
Berkeley's been doing logic optimization since the beginning of time, is my understanding.
Yeah, since I was a student. Yeah. Okay, but there are other tools. For example, there's a tool called Odin 2, which the VTR people have used a lot over the years. Okay, but the point is you can kind of mix and match the pieces if you get all these intermediate formats figured out. Okay. All right, so now what I want to do is let's go look at a little bit about FASM. Okay, we've seen that. So here we go. Let's look at some FASM. So this is some FASM that came out of a tool that we have written. So here's another use case for Project X-Ray. If you have lots of ROMs in your design, big ROMs generally get implemented as block RAMs, right? It's a block RAM that simply has no write enable. So it's a memory, but the bit stream contains the initial contents of the ROM. If you decide after you've been running the design, you'd like to change the contents of one of your ROMs, it's really dumb to go back and have to resynthesize and place and route and bit gen, especially if your design takes overnight for that process. And of course, your guys' experience with, class designs, the process takes 10 minutes. But overnight is not unusual for very large designs that are pushing performance. And so it was proposed by the person who is going to talk on Monday, Tim. He said, it'd be cool if somebody could use what we have in the FASM representation and create a tool so that you could take a bit stream, turn it into its FASM representation, change the initialization contents of the memories, which is what I'm selecting here with my mouse right now. Whoops. Okay. And change those, convert it back to a bit stream, and in 20 seconds, you've changed the contents of your ROM. So we have a program called Project X-Ray-BRAM-Patch, which does just that. And so FASM was very useful because you take your bit stream, you run a tool that's part of Project X-Ray called bits to FASM. You get a FASM file, it's textual. You can go in and modify it if you want. You then go FASM to bits, generate a new bit stream, and you have doctored the bit stream. But you've done it from a safe textual representation. Now, there's a lot of things, you wouldn't be able to add a fourth, microprocessor core to your design using FASM very easily, would you? But this was a perfect use case, right? Go in and doctor those RAM-ROM initialization streams. So if you look at it, it kind of looks, it has some similarities to what we saw elsewhere in the databases, right? Here, I'll make this bigger so that those of you in the back can see it. So here it says, all right, well, the BRAM-L at X6Y5, the RAM-B18_Y0, that's one of the two RAM-Bs or BRAMs at that location, his in-use property is set, presumably indicating that BRAM is being used, thus the name. Okay, you guys know from 220, there was a little bit in chapter 19 about bypass. What do you do if you're reading and writing from a memory at the same address, right? Are you gonna output what was being written or output what was there before the write happened? Since it's the same clock cycle, you get to decide. I believe that's what the read address collision does, okay? The BRAM is configurable for multiple input and output word widths, okay? Some stuff about reset priorities. Okay, we got write widths. There is an output register on the BRAM. Like there's a couple of registers. I don't know if these are in or outputs. I think they might be input registers. Notice they have initialization values. They're 18-bit registers. Okay, blah, 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 and so once again, it looks a heck of a lot like that segbits file, except instead of telling us the frame and bit address to turn on that feature, it says, in your bit stream you've just had me analyzed, this feature was turned on, okay? So it's kind of the opposite. All right, and you can see they're just, all kinds of stuff. Now down here below, what are these? Well, this is a pip. It says inside the int L at X4Y8, there is a wire in that tile called EE2BEG0. And there's a pip between that wire and the EE4N0 wire, and that pip is turned on. Anything that's turned off doesn't appear in the file. So this is just the stuff that's turned on, okay? So it's a pretty nice representation. Here's IO, fast slew rate, input, Are there pull-ups? What kind of input termination, et cetera. So that's FASM. And FASM and X-ray go hand in hand because nobody wants to read the bit stream, which is binary. You don't want to read the database. And so a common thing to do is take the bit stream, convert it to FASM, because you can always go back the other direction and get to where you started. Okay, that's what I had prepared. What questions do you have at this point?
I was just gonna say, you'll notice all of the stuff is just ASCII human readable text, even though the other files that I called .db and we call them databases, nothing's actually in binary format. It could probably be compacted into much smaller files, but it's really nice for us to look at that it's human readable. So.
That's right. And that seems to be a philosophical decision they made in the SymbiFlow project. The leaders of the project said, this is hard enough. Let's not deal with binary files, okay? You can always write something that'll compress a ASCII file down to binary, but for debugging and development, there's no substitute for JSON files and files like this that are, one entry per line. What could be easier, right? No syntax. You don't need to write a parser. You just fire up your Python program and say for line in file, right? And then do something with it. And so that's a nice
These
feature.
files get really big.
Humongous. And so, yeah, you don't want to suck it all in at once.
I tried VS Code, editing, like,
Another thing to note is that in the SymbiFlow Project X-Ray repository, there is a lot of code already written that gives you APIs into these database files. I didn't know about it when I first started. And I just write Python to open this file and read it and do things to it. And then later I realized, no, they've got all kinds of code that you can call that will read the database and allow you to query and pull what you want out, et cetera, et cetera. So you might look for that. It's in a module, I think, that has the word database in it for obvious reasons.
Mostly Python, I guess.
The stuff I ran across was all Python.
Seems like all the scripting they do is Python.
Yeah, so Project X-Ray is a combination of C++, Python, and when they're doing the fuzzing to document the database contents, it's a combination of little Verilog subdesigns, Pickle, Python, and C++. But once you get away from that, most of what I've seen is it's a lot of Python, okay, which fits me quite well because I like Python. Let's see, as I said, if you go to Project X, let's do this right now. If you go to the Project X-Ray repo, and you know that in GitHub, every repo, actually every directory has a readme.md file, right? So here's the one for Project X-Ray. And they have a quick start guide. They tell you once you've cloned it, do this, do this, do this. Makes it real easy to install in general. But as you go down here and you get down, and you make this and you do this, and then you get down near the bottom and it said, oh, by the way, where is it? Where is it? There it is, step 8. If you don't want to have to create a Project X-Ray database yourself, which will take some number of hours on a pretty good machine, they have a little script that'll just go grab the latest database from their repository. And so the files I showed you, I obtained just by running this download latest db.sh script. But if you want to, here's where you go into the Fuzzers directory and you start typing make commands and off you go.
Okay, so basically if you're not doing that, you're basically running all their stuff that does the fuzzing.
That's right, yeah. So
Okay, so
if you want to, you can run the Fuzzers yourself. And in fact,
you run it on something like a part that maybe they haven't done yet.
exactly, maybe if there's a part they haven't done. Now, if you go into their documentation, and we'll see if I can find it here. I saw it as I was preparing. They have find it? We're over time, so anyway, here we go, adding a new fuzzer. So they actually have a fair amount of information on how, if there was something they had not yet solved for, how you would go about writing your own fuzzer to do it, okay? Their fuzzers are all, I mean, most of the fuzzers look quite similar, as you might guess. Create a bunches of designs that all are kind of similar, that have differences, record what the differences in the designs are, take that and combine it with the bit streams that come out to do the differential analysis and, you know, figure out what does what. And so they sort of tell you how you can do it.
And when it's doing the fuzzing, it's using Vivado to generate those?
Yes, yeah, because you're generating real designs. Okay. So a lot of things going on. It's classic open source. If you were interested in this and wanted to, you know, do some on your own and possibly contribute, they welcome it. You know, and it's a very professionally run group. They have very specific rules about what you have to do to get a pull request accepted. They carefully review everything. This isn't a case of anybody can check anything in they want. There are people who are sort of the heads of the group that carefully review. They have fairly strict rules on you have to sign your commits, where you certify that you have not copied any proprietary code. They don't want the case where people have taken proprietary code and incorporated it into an open source project. And there's a way you do that when you do a commit in GitHub. You know, you have to have a appropriate open source license if you're going to add, you know, propose adding new repositories to the overall SymbiFlow umbrella. Yeah, we got a question, Jeremy.
Are there any like open source FPGA architectures, like kind of how RISC-V is?
I'm glad you asked that question. There are people who've proposed open source FPGA architectures. I don't know a lot about them. I think Dr. Wirthlin may know more than I do.
Well, there's a couple of initiatives.
Tell us the names of them.
The Open FPGA one, it's kind of a DARPA sponsored one.
Okay, so DARPA, which is the Department of Defense Advanced Research Project Administration, is sponsoring an open FPGA, and it's called Open FPGA effort.
Tens of millions, right?
It's big, yeah. And so they're, you know, and of course, the open FPGA people need tools. And so guess what they're doing? We keep running across them and working with them as well because, you know, they're working with some of the tools that you've seen in today's talk as well. Yep. Who else? Mike, is there a?
Well, this is the one group that Tim's working with, right? The, what do they call the open, what's the consortium he's?
CHIPS.
CHIPS.
Okay, so there's another open hardware consortium called CHIPS.
We're gonna look at an FPGA.
Which one of their sub projects is open source FPGA stuff. So yeah.
So it's also worth stating that there's closed architectures that use the open tools.
Good point. Please describe that.
So I don't know of any full-fledged FPGAs, but there are
Flex Logic, is it no or no?
micro something.
Semi, not micro.
No, something with micro in the name, I thought. But Tim talked about one guy. I can't remember. But so there's a handful of companies, I don't know, maybe 2 or 3 or 4 that specialize in what we call eFPGAs, which is basically let's put some FPGA stuff in your chip. So whether that's in your processor that you're building or some embedded SoC chip, but let's put alongside your maybe RISC or ARM CPU, we'll put a little bit of FPGA there, and maybe it's only a tiny amount, but then you got to write all these CAD tools, placers and routers and things like that, and so then they go use some of the tools that we talked about. Maybe not X-ray, because X-ray is for Xilinx, but they kind of hook into the same stuff and they use these, what we've often called academic tools, but maybe it's not quite right to call them academic tools when commercial companies are using them for their products, but they're open source tools.
Good. I'm glad that came up. That's a nice angle that we never talk about.
Yeah, I mean, VTR has, I think, 2 or 3 companies using it that they run their own bit gen thing after it's run through VTR. So
So there you have it.